Hello everyone, and welcome. Today, we're going to explore a powerful analytical technique called flame atomic absorption spectroscopy, or FAAS for short. It's a fascinating method that scientists use to find out exactly how much of a specific metallic element, like lead or copper, is present in a liquid sample. Imagine testing drinking water for contaminants. FAAS is one of the tools for that job. Let's break down how it all works, step by step. The main goal of FAAS is to measure concentration. To do this, the instrument has a few key parts. First, there's a special light source called a hollow cathode lamp. This lamp is unique because it emits light at the precise wavelength that only our target element can absorb. So, if we are looking for iron, we must use an iron lamp. Second, we have the flame. This hot flame, typically a mix of air and acetylene, is where our sample gets analyzed. The process begins when our liquid sample is sucked into the instrument and turned into a very fine mist, a process known as nebulization. This mist is then carried into the flame. The intense heat of the flame instantly evaporates the liquid solvent, leaving tiny solid particles. The heat then breaks these particles apart into individual, neutral atoms floating in the flame. This is called atomization. Now for the crucial part, absorption. The light beam from our special lamp shines directly through this cloud of atoms in the flame. As it passes through, the atoms of our target element absorb some of this light energy. This absorption happens because the light has the exact energy needed to excite an electron in the atom to a higher energy level. It's like a specific key fitting a specific lock. Other elements in the flame won't absorb this particular wavelength of light. On the other side of the flame, a detector measures how much light successfully passed through. If there's a high concentration of our target element in the sample, there will be many atoms in the flame to absorb the light, so less light will reach the detector. Conversely, a low concentration means fewer atoms, less absorption, and more light hitting the detector. The instrument then calculates the difference between the initial light intensity and the final intensity. This amount of absorbed light, called absorbance, is directly proportional to the concentration of the element in our sample, based on a principle called the Beer-Lambert Law. By first running known standards to create a calibration curve, we can accurately determine the concentration in our unknown sample. And that, in a nutshell, is the basic principle behind flame atomic absorption spectroscopy. It's a highly specific and sensitive technique used everywhere, from environmental monitoring to clinical analysis and food safety. Thank you so much for watching. If you found this explanation helpful, please consider liking the video and subscribing to the channel for more science content. Your support truly helps us continue making these videos. We'll see you in the next one.